There is no single system of error analysis. The methods shown here are a generally accepted system of error analysis, but when you get to university, please refer to your lab manual for each of your courses to see which system they are going to use. And it may be that your engineering labs may use a slightly different system than your physics labs, which will use a slightly different system than your chemistry labs. You're just going to have to pay attention. In all of the labs, though, experimental error doesn't mean what you did wrong. Experimental errors are not mistakes. They're indications of unavoidable imprecision and are better called uncertainties. For example, let's say you're measuring the length to the end of this pendulum. Take a look at it, pause, and estimate the length. It's certainly closer to 128.9 centimeters than to 128.8 or 129.0. We're at least within half a millimeter, or 0.05 centimeters. Given a similar uncertainty at the other end, lining everything up, we would express the length as 128.9 plus or minus 0.1 centimeters. That 128.9 is called the central value, sometimes written with an x, sometimes written with the variable used to represent the quantity. Could be an L or a D in this case. That plus or minus 0.1 is your uncertainty, sometimes written as a delta x or a delta L, delta D. For a digital readout, the error is usually half of the last digit. And you've probably noticed, if you've taken digital readings before, that sometimes it seems to flicker a little up or down. This could be 12.8 and then flicker to 12.7 for just a fraction of a second before going back to 12.8. That's probably because it's close to 12.77 or somewhere in there. So that 12.8 is really 12.8 plus or minus 0.5 degrees Celsius in this case. Now note that it's good practice to write the central value to the same number of decimal places as the error. So if you're writing the error to 2 decimal places, go ahead and write your central value to 2 decimal places. Now, these read-off errors are instrumental. The dominant error is often procedural, meaning it doesn't come from the instrument itself, but how the instrument was used. For example, the uncertainty in the time for 5 oscillations of the pendulum is dominated by not the precision of the stopwatch, but irregularities, wobbles in the swing, or human reaction time, which is only good to within about 0.2 or 0.3 seconds. For a better estimate of our procedural uncertainty, we perform multiple trials and calculate the standard deviation from the mean. This is assuming that our error is random, not systematic, and would result in a normal distribution. If you've taken the data analysis class, you will have had practice calculating standard deviation. If you have not taken the data analysis class, now is the time to learn how to calculate standard deviation. You can do it out longhand, but you do not have to do this. This isn't data analysis class. I don't need to see your work. You can make your calculator do this for you if it has statistical functions. You don't know how to use the statistical functions? Find the manual online using Google if you search the make and model, and look up how to do mean and standard deviation. Often it's that it looks like an O with an extra little line out to the top right. That's a sigma. You're looking for sigma x or sigma n. Now your calculator will give you your mean and your standard deviation to a ridiculous number of digits. This is obviously absurd. In this example here, we don't have nanosecond precision in our error, and if we're uncertain about the tenths place, why would we bother writing decimals out to the millionth place in our central value? As a general rule, you can round the central value to the rightmost decimal place at which the error starts applying. You could, in this case, round to the nearest tenth and give your time as 3.6 plus or minus 0.2 seconds. It's better, though, especially if you're going to use your measurement to perform calculations, to keep an extra digit for each. It's a good idea to have 2 significant digits in your error. Now, if you have no standard deviation, if your data values were all identical, this doesn't mean you have no error. You at least have your read-off error. In this case shown here, you should state your value as 7.0 plus or minus that 0.1 newtons, the 0.1 from your read-off. It's not perfect, it's not zero error. Now, all of the errors expressed so far have been absolute errors. Sometimes it's useful to express the error as relative to the central value, meaning written as a percentage. We could write 85 plus or minus 3 centimeters as 85 centimeters plus or minus 4%, because 3 is 4% of 85. Just take the 3, divide it by 85. Your calculator says 0.04, that's 4%. Now, when you add or subtract measurements, add the absolute errors. So if you are calculating a quantity z, that is the sum of x plus y, the error in z is equal to the error in x plus the error in y. For example, if you take 5.0 plus or minus 0.1 centimeters and add it to 4.9 plus or minus 0.1 centimeters, we have 9.9 plus or minus 0.2 centimeters. For why this makes sense, think about the minimum possible values of each of your measurements. The minimum possible, if you subtract off that 0.1 each time, becomes 9.7. Similarly, the maximum value, if you take the maximum values of each of those measurements, is 10.1. The average of 9.7 and 10.1 is 9.9, and both our maximum and minimum values are 0.2 centimeters away from that. When multiplying or dividing measurements, we can't add the absolute errors because they're not even in the same units. Instead, we're going to add the relative errors, the percentages. For example, here's a projectile. We've caught it on this image 2 different moments in time at 2 different positions. Now, the instrument was calibrated to take these images 1 millisecond apart, and we had about 3% error in that 1 millisecond. What about the distance? Pause and take a moment to estimate what the distance between these 2 positions is. A good estimate would be 14.5 centimeters, plus or minus, because of the blurring, 1.0 centimeters. That's 7% error. So when we calculate our speed, speed is distance over time, 14.5 centimeters per millisecond, that 3% from our time and the 7% from our distance becomes 10% error in our speed. Now, we take 10% of 14.5, always round up. You want to be generous with your error. This is 14.5 centimeters per millisecond plus or minus 1.5 centimeters per millisecond. And we could convert that to meters per second if we so chose. Now, remember, if you look up how to do error online, you might find different systems. Many university lab manuals will instead use the formulas shown here. We don't tend to use these because beginning students tend to underestimate their error to start with, so we're going for the far outer bounds of what's possible. Now, when taking a root or power of a measurement, we're going to work with the relative error again and multiply that relative error by the power. Here's an example. A square root is, remember, a half power. So our 20% error becomes 1/2 of that, 10%. So once we take the square root of the 25 and get 5, we're taking 10% of the 5, express our final answer as 5.0 plus or minus 0.5 meters per second. Square roots are something we're going to be calculating often. For other functions like sine or tangent, please ask your teacher for the method to use. The error in any conversion factor, however, can be considered to be 0%. Just convert the error. For example, an Italian police Lamborghini has a top speed of 309 plus or minus 5 kilometers per hour. You're not going to win a car chase against the Italian police. This does convert to 309 becomes 85.8, 5 becomes 1.4 meters per second. After we've calculated our error, we're going to graph it using not circles around our data points, but error bars. The error bars are drawn to show the width and the height of possible values. For example, here we have horizontally a value of 0.6. So the dot is at 0.6 across. However, we have an error in that measurement of 0.1, meaning we draw error bars that are 0.1 wide to the right and the left of that 0.6. Similarly, vertically, we have 0.5 with error bars that are 0.2 tall above and below that. Now, we're not going to have just one data point. We're going to have several, and we're going to draw the line of best fit through them to show the relationship between our variables and often to calculate the slope of that line. But note that we're not going to draw a single line of best fit. Rather, we're going to draw a maximum possible line of best fit through the top and left edge of our error bars and the minimum possible line of best fit through the bottom right edge of our error bars. For example, shown here, we could have a maximum slope of 25.0 centimeters per second squared and a minimum slope of 23.8 centimeters per second squared. That would give us an average of 24.4 centimeters per second squared, and our maximum and minimum were 0.6 centimeters per second squared away from that. So we would express our final value for our slope as 24.4 plus or minus 0.6 centimeters per second squared. What if the data is not in a straight line? It will be. That's what we're going to cover in proportionality.